Yes, a good morning and welcome back to our edition for today. Today we shall have, as usual, a combined A-level lesson, and it is going to be on the binomial theorem. I expect that we all attend seriously, with seriousness. However, I want to challenge you to give me feedback, because the previous exercise, that is 14A, I have not gotten a feedback, and that prohibits my progression. I'm going to progress to the next part with an assumption that you grasp that part. We are going to look at a situation where we consider numbers with large powers. Numbers with large powers. How do we handle numbers with large powers? Now, when we are handling numbers with large powers, we use the combination expression. We consider a situation where we bring in the factorial notation. I'm aware that we have not looked at that we particularly need for our facilitation to understand this area. When we have a number like n factorial, mathematically we are going to write it as 1 times 2 times 3 times 4 times, and it goes on up to integer n. It goes on up to an integer n. I will give a quick example that if I have 5 factorial, I will start from 5 multiplying downwards until I reach 1. If I have 3 factorial, this is a factorial that ends. It means 3 times 2 times 1. Now, this is n factorial, so it starts from a small number, which is the minimum, and it goes up to the big number. Now, if we consider the expansion that we looked at, a plus b, remember we are looking at a plus b to the power 2, to the power 3, to the power 4, to the power 5, to the power 6. But now we want to look at it for a very big number of power n, where n can take on any value. From our expansion, we already know that the first term will be a to the power n. Now we are going to write the next term as n combination 1. We shall explain what that means. A to the power n minus 1 times b. The next term is going to be written as n combination 2, a to the power n minus 2 times b squared. There is no big difference here. The technique is that again, when we add the powers between a and b, you should be able to get n on each term. The only difference is that we are bringing in the coefficient and writing it as a combination. What we should be having as a coefficient here and here for this term So you can guess even what we would have for the next term. It would be n combination 3 a to the power n minus 3 b to the power 3. We shall add on the next term. Let me bring it this side. It is a continuation. We have not closed because of the space on my paper. I'll add on n combination r. If I use that, it will be a to the power n minus r now, b to the power r, plus the very last term would be n combination n times b to the power n. Now we are going to define combination n combination. N combination r is the general one. Will be defined as the factorial of n over the factorial of n minus r times the factorial of r. This is read as the combination, as I've been pronouncing it, of n with r. That's how we read it. And C represents that combination. Now we are going to look at what do we mean by that. If I say n combination 1, I mean n factorial. This implies that r is 1 if we compare it with this, over n minus 1 factorial times 1 factorial. And if I use the approach I have given you here, that if it is 5 factorial, I will reduce it. If I was reducing it up to 3, I would say 5 times 4 times. If I stop at 3, I put a factorial there. And if I put a factorial there, I am forced to divide. If it was a division, I would be forced to divide. So if I expand this, because I want to find out what is it equal to, and because I have an n minus 1 factorial down, I will expand it by decreasing it by 1. But since what I have got is similar to what I have in the denominator, I will pause it there so that I can cancel these two and stay with my n out of 1 factorial, which is n. Because 1 factorial is actually 1. And your calculators have the factorial button. They have the factorial button, but of course, like we always do, most students, especially if they have not covered this concept, will not know the use of a function on the calculator unless they have been introduced there. I'm looking for a calculator, and I had kept it far from my bag, so I want to look for it. If you check on your calculator, it's time for you to check. There is a factorial button normally near the control buttons or the direction keys. If you write 1, it's normally a shift. You shift or you press the second function and press the function where you see that factorial button. You should be able to get that the factorial of 1 is 1. That gives us n. In the same sense, for us to get used, we can look for n combination 2. We write this as n factorial over n minus 2 factorial times 2 factorial. And if we want to simplify it, it will be n into n minus 1 into n minus 2 factorial. Why? Because it resembles the denominator part, and I want it to cancel out. So I have that. If this cancels out, I stay with n into n minus 1 over 2 factorial. I'm not going to expand this. If we want n combination 3, I think the pattern is now beginning to build in your head. It is n factorial over n minus 3 factorial 3. So we will expand, and I believe all of us know that when I write this as n into n minus 1, you know that I'm multiplying. Until when I get n minus 3, then I put my factorial there, because it resembles part of the denominator. And then when I simplify this, I'll put it down here. I will stay, this will cancel. I'll stay with n into n minus 1 into n minus 2 out of 3 factorial. If we look at the next term, I'm looking at the terms that we have involved in our formula there up. If we look at the next term that we involved is NCN. What happens to this? It is n factorial over n minus n factorial n factorial. You will discover that 1 factorial is 1. What about 0 factorial? 0 factorial is 1. And 1 factorial is 1. So, it implies that if we expand this, we shall have n factorial over 0 factorial n factorial. And this will give us, at this stage, we shall say, but 0 factorial is equal to 1. So this will give us n factorial over n factorial, which implies that NCN will be equal to 1. Once we have these values known to us now, like they are, we are going to go back into our general equation. And we substitute for them. We are going to go back into our general equation and say, if we substitute in the general equation for combinations, for the combinations we have got, we shall get that a plus b to the power n, I'm getting the final expression, which is going to be important for us, is a to the power n plus, we have said when we have n combination 1, we got n. So I'll put there plus n, a n minus 1 times b, plus n combination 2, we have got it as n into n minus 1 out of 2 factorial times a n minus 2 b squared. We added on the third one, n combination 3, which would be our n into n minus 1 into n minus 2 over 3 factorial, and we have a to the power n minus 3 b cubed plus many other terms, and the last term, as we have seen, our n combination n b to the power n will just become b to the power n. Now this expression here becomes the general expression for large powers, becomes the general expression we'll use for large powers of a binomial number. We will go ahead, I'll go ahead to tell you how do we get this. I want to zoom in close to a few terms. You look at a to the power n. One of the concepts that we looked at is differentiation. If I have the first term as a to the power n, there is no b, but to get the second term, I differentiate the first term. So if I differentiate this, I get n, which you see here on the second term, and the power of a decreases by 1. Do you see that? Then I add a b. To get the third term, which is this, I differentiate the second term. You will see that we have the n which is there times n minus 1. Then a to the power n minus 1, we subtract again 1 to get a to the power n minus 2. And the b is squared. But here we put over 2 factorial. If we differentiate this numerator, the numerator, we get the third term. Because we have already n and n minus 1, we add on n minus 2, we decrease the power by 1, we get n minus 3, but we put it over 3 factorial. So the process goes on and on. If we wanted the next term, therefore, it would have been n into n minus 1 into n minus 2 into n minus 3 times a to the power n minus 4 over 4 factorial. If you are following, you can see that the pattern is okay until the last term becomes b to the power n. Just like it was when we had small powers, the first term will always be, if it, for example, n is 2, it is a squared, and the last term is b squared. And in between there, we have other terms. Now, using this formula, assuming that you have understood my explanation, you will need to master this formula as a student and to know the n combination interpretations. Then we can go on to test how we can use it in a few examples. We can proceed to test how we can use this formula in a few examples. I am moving to page 280 if you have Backhouse 1. How do we use the formula? How do we use the formula? As we prepare to look at the first example, I can remind us that we have said that if we have n combination 4, it can be looked at as n factorial over n minus 4 factorial 4 factorial. But we have said we can expand this and write it as n into n minus 1 into n minus 2 into n minus 3 until we get to n minus 4, and we put a factorial there because it resembles the denominator. Then n minus 4 factorial 4 factorial, and this can simplify to n into n minus 1 into n minus 2 into n minus 3 all over 4 factorial, because this will cancel. Once we know that concept, I repeat, then we are good to go. First example. This knowledge will now allow us to expand numbers with very big powers without having to open brackets. And it will also allow us to find the coefficients of some of the numbers. So our first example is, we are asked to write down the first 4 terms. The first 4 terms of the expansion. Write down the first 4 terms of the expansion. Say 1 plus x to the power 10. 1 plus x to the power 10. We compare this, CF is comparing, with a plus b to the power n, which was our general expansion equation. If we compare this, our a becomes 1, our b becomes x, and our n becomes 10. After comparing this with that, the corresponding values are identified, and then we have that. They are saying to the first 4 terms. So we say, if we use the general expression now, using the general expression will enable it to be to write itself in your mind that our first term will be a to the power n plus, we differentiate, that is n, into a to the power n minus 1 times b, and here it would be over 1 factorial. That's why we don't write that 1 factorial, plus, you don't need to cram this formula once you understand this. Differentiate this, so it becomes now n into n minus 1, a to the power n minus 2, then increase the power of b from the previous by 1. There is a power of b here, but to the power 0, for consistency if you want to understand. Over here, over 2 factorial, don't forget that. Plus, we differentiate again the part that has a, n into n minus 1 into n minus 2, a to the n now minus 3, over 3 factorial times b cubed plus. Because they said the first 4 terms, this is the first term, second term, third term, fourth term. So what we have should be able to give us the first 4 terms. Now at this stage, we have our a, we have our b, we have our n. We basically need to substitute in and say that our 1 plus x to the power 10 therefore will be equal to the a, which is 1 to the power n, plus the n, which is 10, times a, the a is 1 to the power 9, or 10 minus 1 if you want, times b, which is x, plus n, which is 10, into n minus 1, which is 9, times a, which is 1 to the power n minus 2, that is 10 minus 2, over 2 factorial times x, the x is now squared, plus n, which is 10, into 9, into 8, times 1 to the power 7, times x cubed, over 3 factorial plus. We put 3 dots, ideally to signify that it is continuing. Now finally we can compute and rearrange this to get our final answer. 1 to any power will always remain 1. So whether the power is 9, it will always remain 1. So it will be 1 plus 10x, that is the second term. Here we have 90 divided by 2, which will give us 45, by the x is squared, and plus, lastly, we have 90 times 8, that is 720, 720 over 3 factorial. 3 factorial is the same as 3 times 2. Here we put 3 times 2, otherwise you may forget. So 720 divided by 6 will give us 120, and the x is cubed plus 3 dots. So that expansion is obtained just as simple as you can see. Now we can try out one more of that method. They say expand, and they say 2 minus x over 2. And they say to the power 7. 2 minus x over 2 to the power 7. If we are told to expand this, what do? Once we have the formula, which is here, we know that the first term is going to be now 2 to the power 7. The next term we shall differentiate. So 7 times 2, reduce the power by 1, times b. So our a is 2, our b is minus x over 2, and our n is 7. I'm feeding them here, and I'm looking for the first 4 terms. So here I multiply by my b. The next term is differentiate this 6 times 7 times 2 now to the power 5 over, I have a factorial here now of 2 over 2 factorial, but this is subjected to minus x out of 2 now squared. The next term is the first term, that is 6 times 7 times 5. If you want to be systematic, you start writing with a 7, so that it keeps reducing as you see. It will be 7 times 6, then 7 times 6 times 5. Then times 2 will now decrease by again 1 to give us 4. And the term of x out of 2 will now be cubed plus the 3 dots, but here we have over 3 factorial. And when we compute this, we'll get our 128. This will become a minus. This 2 to the power 6 is 64, but if we divide it by 2, we get 32. So 7 times 32 will give us, we know that 7 times 30 is 210, and we have the remaining 2 times 7, which is 14. So we have 224x. This is squared. It implies that it's going to become a positive here, but 2 factorial is the same as 2 times 1. And 2 to the power 5 is 32. Then this 2 squared is a 4. So down we have 32 divided by 8, which will give us 4. And therefore it means we have 28 times 6. 28 times 6 is the same as 164, because 168 if you compute, and this will be x squared. The next term is going to be negative because the term in x has a power which is odd. So it will be minus, and at this stage you have 3 factorial, which is 3 times 2, and you also have 8 there. So if you have a calculator at this stage, you reduce this. 3 factorial will take away the 6. I can say that will cancel, and I have an 8 here, but 2 to the power 4 is 16, so that 8 will give me a 2 here, and then this is 35, so I will have 70x cubed, and you add your 3 dots. This introduces us to one way how we can expand any number that has a higher power without struggling. We can look at the second example. It is still an expand example. It's plus x squared to the power 3 up to the term in x cubed, up to the term in x cubed. Now, when we look at this and compare it with the a plus b to the power n, then we will notice that our a is 1 plus x, and our b can become x squared. Someone must have been saying, now how do we handle this? 1 plus x can be considered to be a, and b can be x squared. And now with this one, if we use the same formula, we shall have the first term, which we have agreed it is 1 plus x. The first term is 1. Okay. We can have this as a situation, but I think if we changed it to 1, it will be very easy for us to handle. Let us change this because a is going to be having a power, it will ease us our situation when we make a 1 and we make b instead x plus x squared. Such that if we use the same expansion, the first term becomes 1 to the power 3. 1 to the power 3 plus the next term, which we saw is n times a. So n is 3. We multiply it by a, which is 1, to the power 3 minus 1 now, times b, which is x plus x squared. Times b, which is x plus x squared. The next term becomes 3 times, this was 2, times 2 now. The next term becomes, it is n into n minus 1, which is 2. Out of 2 factorial times a, which is 1, to the power, this is the power 2, so it will be to the power 2 minus 1, times b. b is x plus x squared, but this is now squared. This is squared plus. Now we will notice one thing. If we proceed, they said up to the term in x cubed. If we proceed, do we still have a term in x cubed when we add on? When we go beyond that point, do we still have a term in x cubed? If I open this, what does it give us? It gives us 1 plus 3 into x plus x squared plus, this is going to give us 3 into x plus x squared plus. Since we are already seeing a term in x to the power 4, I think this will give us what the examiner wants. If we open brackets, we have 1 plus 3x squared plus 3 into, this will give us x squared plus, if we expand this, we have the first term squared plus twice the product, which will be that, plus the last term squared. I think we have another term here that we can get. The other term would be 3 into 2 into 1 times 1 now, when we multiply this, which is 1, times over 3 factorial times 1 to the power 1 into x plus x squared cubed. Yes, this will give us an additional term from here, which incidentally is going to be x cubed. From this term, we are able to get an additional term. 3 times 2 times 1 over 3 factorial. 3 factorial is the same as 3 times 2. So this coefficient dies. But if we open this bracket, the first term we get will be x cubed. It will be the only term that will be to the power 3 that we need. So there is an additional x cubed here that we'll need in that expansion. You are supposed to be able to identify that for you to be able to get the correct answer. So our expansion, 1 plus x squared to the power 3 will actually give us 1 plus 3x plus 3x squared. If I open bracket, I'll get plus 3x squared again, plus 6x cubed plus x cubed. The term in x to the power 4 now is ignored because the condition was up to the term in x cubed. So our answer becomes this, plus 6x squared plus 7x cubed, and we stop our expansion at that stage. That would be our response for that number up to the term in x cubed. Up to the term in x cubed. Now, as an exercise, at this stage I could say expand up to the term in x cubed, and I give you a number. They give you a number like 1 minus x squared to the power 4. 1 minus x squared to the power 4. We will continue to look at another concept. We have mastered how we can expand given a big term. We have seen how we can expand using the combination pattern. Now we want to see how we can get coefficients. How to determine the coefficient of a stated term. Now here the coefficient of the second term is 3. The coefficient of the third term is that. The coefficient of the fourth term is that. Here they say write down. It's an example. Write down the coefficient of the term of the third term of an expansion, say 1 plus x to the power 16. If they say write down the coefficient of the third term, from here we can tell that we have a if we compare it with a plus b to the power n. We have b and we have n. I want you to be very attentive again. They want us to write the coefficient of the third term in that expansion. But if we recall from our general equation, which I will still write, that a plus b to the power n, we have got is a to the power n plus n, a to the power n minus 1 times b plus n into n minus 1, a to the power n minus 2, b squared out of 2 factorial. Now if they are talking about the third term, this is the first term, this is the second term, and this is the third. So we must have capacity to identify the third term. And we say third term is given by n into n minus 1, a to the n minus 2, b squared over 2 factorial. And since we have the a, the b, and the n, we are interested in the coefficient. The coefficient will be the figure before the variable of x. So we can get the coefficient, therefore, by substituting. Our n is 16 into 16 minus 1 times our a, which is 1, the power 16 minus 2, times our b. Our b is x squared over 2 factorial. We compute this. 16 times 15 out of 2 is the coefficient. Therefore, the coefficient will be 8 times 15, and this will give us 120. The coefficient will give us that. They can ask us to find the coefficient of the fifth term. Fifth term of 2 plus 3 out of 2x to the power 8. Now, whenever they talk about third term, fourth term, fifth term, there's one thing that is becoming clear. For example, if we are to look at the value of x that we would get alongside here, it is x squared. It is x squared. And this would be x squared. This is the coefficient. So the x squared is not interested. We are not interested in it. But the third term, as you can see, has a power of x as 2. So if they talk about the fifth term, it means the power of x will be to the 4. Fifth term implies that x, the term in x to the power 4. They want the coefficient there. So we compare with 2 plus 3 out of 2x to the power 8. Compare it with a plus b to the power n, so that we are able to pick our a, pick our b, which is 3 out of 2x, and pick our n, which is 8. After picking our terms, we note that if we need AB is going to be 2 times 3 out of 2x, which will be 3x, if we need it. Now the term with x to the power 4 in this situation is going to be obtained by, if we look at the formula, x to the power 4 will be obtained when we have 4 factorial down. If we have the term to the 2, we have 2 factorial. Term to the 3, we have 3 factorial. So it means this power is going to be reduced. This 8 is going to be reduced by 7, by 6, up to 5. Because remember, the first term will not have the 8. It will simply be 2 to the power 8. So we begin using 8 on the second term, use 7 on the third term, use 6 on the fourth term, and use 5 on the term with x to the power 4. The first term does not have an x. So the second term has an x, the third term has an x, but the powers of x will keep on increasing. Now, it means this will be that, and then our b, this will just be the notation out of our 4 factorial times now our a, which is 2, and this 2 will be to the power 4, since we are looking for the fifth term. As you may note that when we are at that stage, the power of n is subtracted by the factorial we have. So if we have 8 as the power and we take away the term we are looking for, which is the fourth term, the coefficient of the fifth term is the fourth term for the expansion. This is the fourth term. So it will be 8 minus 4, which will give us 4, times the value of b, which is 3 out of 2x. This will also be to the power 4. If you cannot pick this direct, then you remind yourself of that expansion and say the first term will be that, the next term will be that, the next term, this one has a b, the next term will be that, into a to the power n minus 2, the b will be squared, and you will have a 2 factorial. The next term you go again, this into this, a will be, you take away 3 over 3 factorial, and you have b cubed. And the next term, which is what we are using, would be n into n minus 1 into n minus 2 into n minus 3, a to the power n minus 4, b to the power 4 over 4 factorial. If you cannot figure this out direct, then you may need to keep doing this. But how long will you do it? Especially if the power is very big. That's why we came up with a formula. That's why we came up with a formula, any combination. we came up with the formula of n combination R being equal to n factorial over n minus R factorial. If they are looking at the fourth term, we will look at the fifth term, we will look at that formula there. So we are using this. And if we are using this and we want the coefficient of the fifth term, we definitely now simplify this. But as we simplify this, we notice that this part can be written as 8 combination 4 times 2 to the power 4 times 3x out of 2 to the power 4. It can be summarized to look like that. 8 combination 4 times that. And if we use now the combination interpretation, we discover that we are having our 8 factorial over 8 minus 4 factorial times 4 factorial times the 2 to the power 4, which is 16, times the 3 to the power 4. This is over 2 to the power 4 also, the 3 to the power 4 here. And this is to x to the power 4. Since you are interested in the coefficient, the 8 factorial can be expanded. This is just to show you. 8 times 7 times 6 times 5 times 4 factorial, because 8 minus 4 is 4 factorial, 4 factorial, for one of these to cancel, times this will be 16. 16 times 81 out of 16, x to the power 4. So this will cancel. And same as 81, x to the power 4. So the coefficient we want ideally will give us, I can say this will go with a 6, and this 4 will go here 2 times. So we have 14 times 5 times 81, x to the power 4. But 14 times 5 is 70. 81 times 7 is 567. So you'll find that this will give us this as the coefficient we are looking for will be 500. That is the coefficient. The coefficient you are looking for becomes that. The coefficient we are looking for becomes that. Now, if you have really understood, one more number, and you should be ready. You should be ready to actually do the preceding exercise. One more number, and we declare that this is now history. But we will only confirm that is history if you are now able to actually do the next number correctly. You are now able to do the next number correctly. They can say, find the coefficient. Find the coefficient of the term in x to the power 5. Find the coefficient of the term in x to the power 5. In x to the power 5, that is 1. And the 1 in x to the power 6, and hence find their ratio. Find their ratio, and we can say find their ratio. And they give you the expression. If they want you to find the coefficient of the term in x to the power 5 and in x to the power 6, they can give you a question related to find. Now I'm going to use 3 plus 2x to the power 20. Assume this is what they have given you. And they want you to find the coefficient of the term in x to the power 5. What are you going to do to find the coefficient of the term in x to the power 5? I want us to just try out the first one. We have said a plus b to the power n is compared now with 3 plus 2x to the power 20. Our a becomes 3, our b becomes 2, x, our n becomes 20, remember. If I am interested in the term in x to the power 5, what is going to be my combination? My coefficient of the term in x to the power 5. If you have understood the previous one, if you want to find the coefficient, the previous example wanted the coefficient of the term in x to the power 4. In x to the power 5, we shall use the power that we have here, which is 20. So we shall use 20 combination 5. 20 combination 5 times. Now, the term we shall multiply it, we shall look at is the first term here, which will be 3. And if we are taking the combination 5, it will be to the power 5 also, times the b, which will be 2 to the power x, and it will also be to the power 5. That is ideally the quick interpretation. That the coefficient of the term we want is embedded in here. Therefore, summarily, the coefficient of the term in x to the power 6 will also be, look at the power, combination 6. The value of a will stay the same, times 2x to the power what? And if I may just do one, and I will ask you to complete that one, and probably maybe show you one last one. This will be 20 factorial over 20 minus 5 factorial, 5 factorial times 3 to the power 6 times 2 to the power 6 times x to the power 6. So the coefficient we want is what we get from there. But this is going to be reduced until you get 15 times 17 times 16 times 15 factorial. Why? Because we have 15 factorial here, 5 factorial, then times 3 to the power 6. This is the same as 3 to the power 4, which is 81, times again another 3 times 3 times 9, then times 2 to the power 6, which is 64. So if we compute this, which will allow this to cancel out, 5 factorial is 5 times 4 times 2 times 3 times 2 times 1. When we reduce this fully, 5 times 4 is 20, 3 times 2 is 6, we can reduce that 6 with 18 to get 3, so we have 57, which is 19 times 3 times 17 times 16 times 81 times 9. This should be able to give us the coefficient of the term in x to the power 5. This was the term in x to the power 5. In x to the power 5. So using that approach, it becomes very easy for you to get these coefficients. Last, before I announce the exercise, we could probably look at one with a bigger power. If I have 2x minus 3, and this is to the power 14, and I tell you to find the coefficient of the term in x to the power 10. In x to the power 10. I said, by comparison, we should be able to pick the a and the b. And this is written as 2x minus 3, remember. So I can still pick my a as 2x, and this time pick my b as negative 3. And I will still be able to get the answer, because of the arrangement that it is in the form of a plus b to the power n. And I pick my n as 14. So since I want the coefficient of the term in x to the power 10, and I have put my x as a, you must take a big precaution. It means that if I am using my n combination r times a to the power n times b, that approach, I am going to use my n combination r would be times a to the power n minus r this time, y times b to the power r. Why am I using this? Because it is my a that is now going to bring in my power of x. It is my a that is going to bring in my power of x, not my b this time. So if I use this approach, I will use 14 combination 4 times the a, which is 2x to the power n minus r, which is going to be 10, times my b, which is negative 3 to the power r. Our r is definitely 4. And once you are able to figure out this, then it means you have the coefficient that they want. Of course, this is 14 factorial over 14 minus 4 factorial, 4 factorial, times 2 to the power 10, times x to the power 10, times, this is the same as negative 3 to the power 4, which we know will be 81 anyway. Now, if we are at this stage, this, remember, will be 10 factorial. So I'll have 14 times 13 times 12 times 11 times 10 factorial there. I'll divide this by 10 factorial times 4 times 3 times 2 times 1 times our 2 to the power 10 can be written in other ways. We can write it as 2 to the power 5 times 2 to the power 5 to simplify work, times 81. Yeah, 2 to the power 5 is 32. So this 10 factorial will cancel. 4 and 3 can go with the 12. And I can reduce this here to 7. So I'll get 7 times 13 1. X to the power 10 is there, but we are interested in the coefficient. So when you compute this, it should be able to give us the coefficient we are looking for. It should be able to give us the coefficient we are looking for. 77 times 13 times, when this is computed alone, it gives us 82944. At this stage, use your calculator, and when you use your calculator, this, I think, should end up giving you a figure of this. So the coefficient to the term in x to the power 10 becomes this. We shall bring our lesson to the end now, and I therefore announce that you should be in position to actually do exercise 14b. 14b, the book is Backhouse 1. The book is Backhouse 1. I wish you a good weekend. However, you are reminded to check your answers. Should they disagree with what the book is giving you, please inbox me or get in touch with me so that we can identify where you have failed and do as we have been doing. Thank you very much. God bless you. Enjoy your weekend. We'll meet on Monday again. I will be announcing the venue and time. Thank you.